In this lecture, we'll discuss about the introduction to sequential circuits. The sequential circuits are two types: synchronous sequential circuits, asynchronous sequential circuits. First, we'll see the definition of a sequential circuit. The coming output of a sequential circuit de depends on the existed output and the present input. The existed output is also called present state of the circuit, and compared to coming output, this present state is the previous output. Okay, so here we can see the equivalent circuit of a or block diagram of a sequential circuit. It contains combination circuit plus memory elements with feedback. So combination circuit plus memory with feedback become a sequential circuit. Okay, suppose if this memory element is a latch, then latch nothing but gated latch, then this sequence circuit become asynchronous sequential circuit. If this memory element is a flip-flop, then this sequential circuit become synchronous sequential circuit. Okay, see here for combinational we are applying input, and here we are taking output. The same output we are feedbacking to memory, and to the memory we are applying clock signal also. This memory output again we are connecting to input of combinational circuit. Okay, so if this memory is working with levels, then it will become latch, gated latch. If this memory working with edges, then it will become flip-flop. Okay, so the examples for asynchronous sequential circuits: a sequential circuit made with latches, and whatever the sequential circuit contain flip-flop, those all are comes under synchronous sequential circuits. For example, registers, counters, state machines, these all are synchronous sequential circuits. So we are using memory elements in sequential circuits. That memory element can be gated latch or flip-flop. Okay, so these gated latches and flip-flops are basic memory cells or basic memory elements. They can store 0 at one time and 1 at another time. So they are storing two different bits. That's why these are called bistable elements. Okay, generally we construct non-gated latches with NAND gates and NOR gates. We don't use NOT gates because NOT gate contain only one input. We cannot give feedback because there is no other input, and we don't use undo or XOR XNOR also. Okay, these latches and flip-flops both contain gates only, like combination circuits, but because of feedback nature we are getting memory nature. Okay, so synchronous sequential circuit means we can see the change in output, or we will get the output only at a particular clock edges, either positive or negative. Asynchronous sequential circuit means we can see the change in output, or we can get the output at any instant of clock level. Okay, that is the meaning. So here we can see one diagram to understand the exact difference between gated latch and flip-flop. Here I taken D gated latch and D flip-flop comparison. This top diagram is about D gated latch. This below diagram is about D flip-flop. These diagrams are called timing diagrams, timing waveforms. Okay, so this latch working with positive level, this flip-flop working with positive edge. Okay, here I am giving clock. So this is the positive level duration, and this is the data input. We know D flip-flop or D latch produce same output as input. Okay, so during this positive level duration, whatever the data input, that will come exactly at the output. And here positive level duration is ending, and here the data input is high. This same high will continue for this negative level also. See, here it is ended with high, that same high it is continuing, so it is holding, latching logic 1. Okay, now again here positive level started. In this positive level duration, whatever the data input, that will come exactly, and here it is ended with low. This same low will continue for complete uh, this negative level duration, so it will hold to logic 0 here. Okay, so only this is from here to here, this is the complete cycle. Only in the half cycle we are able to store. So this is about latch, gated latch. Now we'll come to flip flop. Okay, so this is positive edge, and here the data input is high, so output also become high until coming positive edge. Until coming positive edge, whatever the high it is there, that same high will continue. Okay, now again here second positive edge, here the data input is low, this same low will continue until next positive edge. Okay, this is the behavior of a flip flop. So we take in same clock, same data input, but output is different compared to gated latch and flip flop. So here in this complete duration of full cycle we are able to store. This is high means it is set, it is storing 1. So that's why flip flop is a full cycle storage element. I hope in this diagram you can clearly see the difference between gated latch and flip flop behavioral with help of this timing diagram. Okay. In this lecture we'll see the definition of a sequential circuit. Suppose there is some circuit, somebody already used it. Let us assume that is a sequential circuit, so it contains memory. Okay, so now you take in that circuit and you are applying your input. When you applying your input, that circuit already contains some output, because already somebody used it, so it stored some output. Whatever the output now you getting, now you will get, that depends on your input and already existed output. Okay, already existed output is called present state, or if we compare that present state already existed output with the coming output, that is called previous output. The coming output become the present output. Okay, so in sequential circuit, the coming output is nothing but next state, depends on the present state and the present input. Okay, that present state some people also call previous output. That previous output is coming due to previous input only. Some people use like that also. Okay, in this lecture we'll see the differences between synchronous sequential circuits and asynchronous sequential circuits. So this is the block diagram of a sequential circuit. If this memory element is a latch, gated latch, then it will be this whole circuit will become asynchronous sequential circuit. If this memory element is flip flop, nothing but working with edges, then this whole circuit become synchronous sequential circuit. Okay, and whatever the sequential circuit which contain gated latches or non-gated latches, that comes under asynchronous sequential circuit, and whatever the sequential circuit that contain flip-flop comes under synchronous sequential circuit. Okay, so here in this memory element we use gated latch. Okay, that gated latch contain non-gated latch. Okay, or we use flip-flop, that flip-flop also contain non-gated latch. In this lecture we'll discuss about level sensitive versus edge sensitive, or level triggered versus edge triggered. See this diagram. Suppose this is for flip-flop, this below one. So here this is positive edge. In the positive edge the input value, data input value is high, and this is D flip flop, so output also will be high. Okay, now this high will continue until next coming positive edge. At this positive edge only we can see the change in the input. So here what is the input? Low, so it is going to low. Suppose here also if it is high, it may continue to high, but because of input is low, we can see the change here. So that's why edge sensitive, we can see the change in output only at edges. That also depends on the input. Okay, now we'll see level sensitive. This is for gated latch. Here also I taken D gated latch. This is also positive edge, positive level triggered. Okay, below one is the positive edge triggered. So in this positive level triggered, here this duration is positive level. Initial in this duration, whatever the input, that will come as it is, because this is the D flip flop. Okay, so here in this duration we can see the changes in the output. It is going to high low high low. It is not like here, it is not maintaining constant between edges, but here it is changing. So we can see the change in the level duration. So this is level sensitive. Okay, for positive level we can see changes in positive duration only. That also depends on the input. If input changing, we can see the change. Okay, but during negative we cannot see any change. It will hold during negative. Latched means holding. So here in the positive duration it is ending with high, so that high only will continue. Okay, so for positive level triggered circuit we can see the change during positive level only. That also depends on input. During negative level, for positive triggered circuit, during negative level we cannot see any change. It will hold. Okay.
In this lecture, we'll discuss the working or operation and construction of SR non-gated NAND latch. We can simply call NAND latch also. Okay, so this is the logic diagram. Here, we need two NAND gates, two input NAND gates. One of the input of this NAND gate is connected to S, and one of the input of this NAND gate, below NAND gate, connected to R. And this NAND gate output is Q, this NAND gate output is Q bar. This Q we are taking and connecting here, and this Q bar we are connecting here. So this is called cross coupled connection. So this is the construction of a NAND latch. Now we'll see the working. So generally this is the truth table. How we got this truth table I will explain very detailed. Okay, first we'll see the truth table format. So there are two inputs, so four combinations will come: 0 0, 0 1, 1 0, 1. And there are two outputs. I listed two outputs. So for 0 0 I am getting 1 1, and for 0 1 I am getting 1 0. For 1 0 I am getting 0 1. For 1 1 I am getting 0 1 1. Okay. So here this is the state or state name or condition name. So whenever both are 1 1 output, both are 1 1 are same, that is we consider as invalid condition, because both outputs should be complementary. Okay, that is the condition. So it is violated that condition. That's why it is invalid or not used condition. This is not useful as memory, because ultimately this latch is for storage. Okay. So this condition we treat as set. Set means whenever, so these three conditions are called valid conditions because both are complementary. See here. Okay. These three satisfied the condition of complementary. So these three we consider as valid conditions and memory conditions. Okay. So in this condition I got 1 0. Whenever we got 1 Q, that we consider as 1 is stored. 1 means set. Okay. But why we are not considering Q bar? This Q bar is just a complemented version of this one. This is same as this one, just it is in the complemented version. Both are same. That's why we are considering only one. Okay, so here in the third condition 0 1. Now 0 stored, so this is we called reset. 0 means reset. Okay, then next again 0 1. So previously 0 1, now also 0 1. It is maintaining as previous. So whenever it is maintained as previous, then we call hold or latch or no change. Okay, right. But out of 4 combinations, I told this we don't use. These 3 are memory. But out of these 3, these 2 are same. That's why you can neglect one. You can consider this one. So finally, we will consider this set condition and reset condition. In set condition, 1 is storing. Reset condition, 0 is storing. Okay. So now we'll see how we are getting these q bar values, invalid, set to reset to hold, everything we'll see step by step. Okay. Now the first condition, s equal to 0, r equal to 0. See here, I listed that condition, s equal to 0, r equal to 0 is the condition 1. Okay. So here I am applying S0, R0. It means this NAND gate, one of the input is 0, but we don't know other input. Here also one of the input is 0, but here we don't know other input. Even we don't know other input here and here, based on the single input, we can predict the output here. Okay. By using NAND gate definition. What is the NAND gate definition? If any one input is 0, then output become 1. Here also any input 0, output become 1. So here output become 1. Q also become 1, Q bar also become 1. So this is happening in the first condition. Okay. And I told both outputs should be complementary. That is the rule. So it's not following that rule. That's why we call it as invalid or not used condition. Okay. Now we'll see second condition. See what is the second condition? 0. See here 1 1 we got for the first condition. Okay. Now 0 1 second condition we'll see. 0 S0 R1 is the second condition. But in second condition, I will explain with the different cases. This is the case 1. Okay. But in all cases, this input will be S0 R1 only. Okay. So here S equal to 0, R equal to 1. And what about these values? I feedback the previous condition values. So previous condition values 1 1 now output values. So now those 1 1 came here. Okay. Now what is the output of this gate? If any one input is 0, output 1. Here both are 1s, output is 0. Okay. Right. But we should not write this output immediately in the truth table. Okay. We have to check whether this output is stable output or not. Okay. Stable output means I will keep this 0 1 input as it is. Then I will feedback these values. When I feedback these values also, again I am getting 1 0, then that is the stable output. That stable output we have to write in the truth table as final output. Okay. So that's why in the next case, this is the second condition only, but the second case will feedback this case 1 values. Then we'll check whether it is stable output or not. See here, second condition case 2 also my S0 R1 only. I feedback the previous values. What are the previous values? Q1. This Q1 will come here. So Q1 came here. And this Q0 will go to top. See, this Q0 went to top. Okay. Now both are zeros, so output is 1. Both are 1s, output is 0. So here we are getting Q1, Q bar 0. Previously what we got? Q1, Q bar 0. So this is the stable output. Now this output is the final output because this is the stable output. We have to take only stable output in the truth table. Okay. And I told out of 2 outputs, we consider only 1 because this is just a complemented version. Both are same only. Okay. And latch is a 1 bit storage element. We just need to store 1 bit. Okay. That's why I'm considering 1. This is called set condition. Set condition. So what we got, see? in the second condition, when I apply 0 and S0 R1, I got Q1, Q bar 0. That's why set. I am considering Q set. That's why I highlighted. Okay. So we are storing 1 here. Okay. Now we'll see third condition. S1 R0. Third condition we'll see. In this third condition also, we have to check with the different cases until getting stable output. So this is the condition 3, case 1. S equal to 1, R equal to 0. S equal to 1, R equal to 0. So this is 1 S1, this R0. What about this 0, 1? Previous outputs. What are the previous output? Q1. That Q1 will come here. So here. And Q bar 0 will come here. Previous Q bar. Okay, right. Now if any one 0, then output 1. If any one 0, output 1. Here both are same. So we should not consider this as invalid. We have to check if I feedback these 1 1 again, whether output changing or not, that I have to check. But in case condition 1, why I have not feedbacked? Even we do feedback, we will get same. That's why, that is the reason. It means whatever I shown for the condition 1, that is the stable output, final output. Okay. So now we'll see case 2 for condition 3. We'll feedback these output values, but this input will remain as same, 1 0 only, S1 S0 R0. Okay. So when I feedback previous case outputs, it will become like this. So both are ones, output 0. Here at least one is 0, so output become 1. Okay. But we don't know whether this output will maintain stable or not. So that's why again we have to check case 3. Okay. So now case 3, again I will in case 3 also I will maintain same S1 R0. I feedback previous case output. So now I am getting both are 1, so output 0. Both are zeros, output 1. So it is stable, because in case 2 what we got? Q0 Q bar 1. Here also we got Q0 Q bar 1. So this is the stable output. So we have to take it as a final output for condition 3, and we have to note down it in truth table. So for S1 R0, what is the output? See, for S1 R0, Q equal to 0, Q bar equal to 1. So we are storing 0. 0 means reset. I told we are taking only Q. Okay, I told the reason why we are not taking Q bar. Okay, but some other applications, based on the applications, we can take Q bar also. We can neglect Q. For example, in 555 IC timer, I observed there we use RS flip flop. There we take Q bar. So according to the application, we take any one. Okay, here I consider Q. Okay, then we'll see last condition. What is the last condition? 1 1. What is the output of this last condition? We'll see. This condition is the condition 4. Here also we have to take a stable output. For that we have to check different cases. So here the input values are 1 1, and I fed back previous case outputs. So this 1 0 will come here. So now both are 1s means output 0. Any 1 0, output 1. Okay. So now we'll check this output is stable or not. Again we'll feedback. When I feedback, I am getting same. So this is the stable output. I will note down this one. Okay. I will note down this one. We'll go to the truth table. So here 0 1. For 1 1, input 1 1, I got 0 1. Q0, Q bar 1. When I observe this one, this 0 1 we got previously also. For condition 3 also. So for condition 3 and for condition 4, we are getting same output. So condition 4 maintaining same output as condition 3. So in sequential circuit, if you are maintaining previous output or same output as previous, then we called hold. That's why this is called hold or latcher. No change. There is no change, it is the same as previous. Okay. So here you may get confused between stable output and hold. Hold means when we compare different conditions, that is hold. Okay, stable means in the same condition. Suppose when I take condition 2, case 1 and condition 2, case 2 itself. In the same condition, when we comparing outputs, that is called stable. But when we compare in different condition, that is called fault. Okay. So this is the working of a NAND latch. SR, non-gated NAND latch. In this lecture, you will see why we consider only one output in latch or flip-flop. We know there are two outputs for latch or flip-flop, Q, Q bar. Of course, we can name other names also. But out of Q, Q bar, we mostly consider Q. Okay. So why we consider only one output? That we will discuss. Out of two outputs, why we consider one? And one more thing, why we consider Q only? Why not Q bar? Or do we need to consider only Q always? Okay, that also we'll discuss. So if we observe Q1, Q bar, whatever the output we are getting at Q, it's a complemented version we are getting at Q bar. Okay, so it's almost same, just it is a complemented version. That's why we can take any one. Okay, and mostly we consider Q, but it doesn't mean we always should consider Q. We can consider Q bar also. Suppose if you take a 555 timer IC logic diagram, there we use SR flip flop. So there we are taking a Q bar. Okay, so based on the application or design, whatever we want, we can take. Okay, right. Okay, some of my students asking, sir, whether it is SR latch or RS latch. Okay, so we can call it as SR latch or RS latch. Whatever the first lecture I uploaded, that I named as SR. That is SR NAND, non-gated latch. So here, to clarify you, I taken as RS, non-gated NAND latch. Okay, now we'll see the difference between the two SR and RS. Okay, suppose here first condition I taken like RS, so both input 0 0, here we get invalid. Even when I take SR also, therefore 0 0 we got invalid. Okay, then coming to second one, second condition. In second condition there I did two cases, here also I did two cases to get a stable out. Okay, so here if you observe carefully this first condition, wherever I kept yes, straight to that I kept Q. Wherever I kept R, straight to that I kept Q bar. But in first lecture, S is on top and Q also on the top. Okay, here and there also, wherever S is there, that straight to that you have to keep Q. Okay, that you can remember. Okay, we are interchanging inputs, so you can you have to interchange outputs also. Okay, that you have to remember. Now, second condition, first case, here I am giving R0 S1. Okay, I will take first condition output as feedback, then I will get to 1 0 Q bar 1 Q 0. Then to know the stable output again, I will apply 0 1 S0 R1 and I will feedback this case 1 outputs, then I am getting stable output. So it means when I apply R equal to 0, S equal to 1, what I am getting? Q 0. Okay, Q 0. So there also in the first lecture in SR, when I take S equal to 1, R equal to 0, what I got? Reset. Q 0. Here also I got same, na? Okay? Right. So, one thing we have to observe, one shortcut. So, when both inputs are different, different means S equal to 0, R equal to 1, R equal to 0, S equal to 1. Whether it is a SR latch or RS latch, whatever the R value, that will come to the Q. Whatever the R value, that will come to the Q. But this condition applicable whenever both inputs are different. Okay, right. Next condition, third condition, when r equal to 1, s equal to 0. Here I taken 3 cases to know the stable output. So here also you can observe, whenever s equal to 0, r equal to 1, we are getting set. In SR also we get set now, when s equal to 0, r equal to 1. And here also you can observe, inputs are different and you whatever r value, that only coming to the Q. Okay, right. So finally, last condition, when both inputs are 1, 1, I taken 2 cases to know the stable output. This is the second case. So whatever the third condition final output, stable output 0, 1, that only I am getting. In fourth condition, second case. So this is called hold. Okay. So this is the explanation about SR and RS. So before seeing this lecture, you have to see first lecture, SR non-gated NAND latch. Then only you can understand this properly. Okay. So in that lecture also see, when inputs are different, whatever the R value, when inputs are different, so this is the condition to final case. When inputs are different, whatever the R value, that only coming to the Q. Okay. So here also straight to yes, there is Q. You have to write like that. So in condition 3, this is the final case. Whatever the R value, that is coming to the Q. Here also yes, and straight to that Q. Okay, right. In this lecture, we'll discuss about SR non-gated NOR latch. Okay, so in this we need two input NOR gates. Okay, one thing we have to observe comparing to NAND latch. Generally, in NAND latch, straight to the yes we write a Q, but here straight to the yes we have to write Q bar. That we have to observe. Okay. Some people assume this inputs as SR or XY also, and outputs as Q bar, or we can name some other names also. Here I named as Q1P. This P is nothing but Q bar here. Okay. So these are the constructional details. Now we'll see the operation step by step. So this is the truth table. Here SR 2 inputs and we will get 4 combinations. Okay. So here I have not started with 0 0. As I started in SR NAND latch with 0 0. Here I not started with 0 0. Okay. Because the reason is NAND latch will be in invalid state when we apply 0 0. Okay. So if we want to make it valid or useful, we should change any one input. Whenever the inputs are 0 0, even we feedback output many times, it will be it will maintain same output. Okay, we cannot go to valid state from the invalid. Okay, so here in a NOR latch, if we keep this circuit in 1 1, when we apply input 1 1, it will be invalid. Okay, so whenever we want to make it useful, we have to change the input values. Okay, and one more reason, suppose if initially if I apply 0 0 to the NOR latch, what will happen? We don't know second input. Suppose here if I apply 0 0 here, I don't know second input of each gate. Then I cannot predict output. Okay. Because there is no output also at that time to feedback. Okay, so we have to start from 1 1. Okay, so even with 1 1, even there is no second input, we can predict the output based on the NOR gate definition. Because in NOR gate, if any one input is 1, output is 0. Like that we can predict. Okay. And here you can see I taken Q here, Q bar here. Okay, these are the state names. Okay. Now we'll see this operation step by step. So initially input both are 1 1 inputs. Okay, output is 0 0. Okay, this is invalid. I told now both outputs should be complementary. Okay, so you have to see this lecture after watching yes or NAND, then only you can understand it properly. Then coming to second condition, S equal to 0 or equal to 1. Okay, so here I have started immediately S equal to 0 or equal to 1. Observe this. Okay, now 1 initially in first case I am getting Q bar 1 Q 0. Then when I feedback with the same input maintaining, when I feedback this case 1 outputs, I am getting Q bar 1 Q 0. So it is stable output. So I am taking this as final output. See here what is coming when S 0 Q is 0. When S equal to 0 Q equal to 0. This is called reset because this is my Q. 0 is stored. Okay. And here you have to observe in SR NOR latch output will be same as S, but in NAND latch output will be same as R when inputs are different. That you have to observe. Okay. Okay. Now we'll see next condition. Third condition. So here my S equal to 1 or equal to 0. When I feedback the previous condition output, I am getting in case 1 0 0. So I have to look for stable output. So I again fed back with same input maintaining. Then I got 0 1. It means Q1 Q bar 0. Then again in third case I maintained same inputs and fed back the second case, third condition, second case outputs. Then it is maintaining same. So it is stable output. So I will take this as the final output for condition 3. So when S equal to 1, Q is 1. Q is 1. Okay. When S equal to 1, see when S equal to 1, Q is 1. So it means 1 is stored. It is called set. Okay. Right. Then last condition. Now 0 0 I am applying. So when I fed back, I got 0 1. And when I check for stable, I got 0. So this fourth condition output same as third condition. So this is called hold. So when I applying 0 0, circuit becoming hold. So when we compare NAND and NOR latches, so when we apply 0 0 in NOR, it is becoming hold, but in NAND it will become invalid. And here when we apply 1 1, NOR becoming invalid, but NAND become hold. And when we apply S0, NAND becomes set, but it is becoming reset. And NAND become reset when we apply S equal to 1. But this is becoming set. So these we have to observe. Okay, right.
In this lecture we will discuss about active low latch and active high latch. The non-gated NAND latch is called active low latch because if we observe the truth table of this latch is invalid or unused when the inputs S are equal to 0 0. It means when S are equal to low, this is in invalid condition. To make it useful, valid, we have to change any one input. Okay, so NAND latch, non-gated NAND latch is called a active low latch, and a NOR non-gated latch is called a active high latch. Because if we observe the truth table of NOR, it is invalid when inputs are high, active high, or 1 1. Okay, so to make it useful we have to change any one input or both inputs. Okay, this lecture in this lecture we'll see the comparison between gated latches and non-gated latches. So this non-gated latches won't contain clock or enable, but gated latches contain clock or enable. Okay, non-gated latches are NAND to NOR. Okay, there is no positive, negative, there is no triggering in non-gated latches. But if we take gated latches, there is SR, D, JKT, and they are positive or negative level triggered. Okay, there is a triggering here. And we use, when we constructing gated latches, we use non-gated latches as latch part. Okay, so both gated and non-gated latches are asynchronous, because in non-gated latches there is no clock, so there is no timing synchronization, so that's why they are asynchronous. But in gated latches there is a clock, but it will work with the levels, that's why asynchronous. Even there is a clock, asynchronous, because of working with the levels, there is a change in the output at any instant of the level. Okay, that's why asynchronous. Okay, in this lecture we'll discuss about S bar or bar latch. Here I taken non-gated SR NOR latch and I connected inverter to S, so it became S bar, and I connected inverter to R, it became R bar. That S bar and R bar values going to that NOR latch, non-gated SR NOR latch. Okay, I actually give SR values, they will become invert and they will go to NOR latch, so that I will get output accordingly. And here straight to the S and S bar I have to connect Q bar, that is the construction of NOR latch. And in the symbolic diagram you can see, if I show SR you have to use bubbles, but if I show S bar R bar you no need to use bubbles. Okay, now we'll see working a truth table. I just taken the truth table of normal SR NOR latch, non-gated. Okay, so this is the truth table. I already uploaded this lecture, you can go through this. After watching this lecture only you have to see this lecture, then only you can understand. Okay, same here we can see when SR equal to 1 1, circuit becoming invalid, and when SR 0 1, circuit becoming reset, when SR 1 0, circuit becoming set, when both inputs are 0 0, circuit becoming hold. So you have to remember these conditions, then come to this S bar R bar truth table. So here first I take an SR value, so when I apply 0 0, what it will become? S bar R bar 1 1. So when we apply 1 1 to NOR latch, what will happen? Circuit become invalid. So when we apply 1 1, see, go back, when I apply 1 1, see what is the state? Invalid. Okay, like that when I apply 1 0 SR, then S bar R bar becoming 0 1, so circuit becoming reset, and when I apply 0 1, S bar R bar becoming 1 0, circuit becoming set. So this is the Q value. Okay, when I apply 1 1, finally S bar R bar becoming 0 0, so circuit becoming hold. Okay, this is the operation of S bar R bar latch. In this lecture we will see another way of drawing latch, that is non-gated latch. For example, I take an SR non-gated NAND latch. So this is the logic diagram. This diagram we can draw another way also, that we'll see now. See, this is the diagram. It means I taken one 2 input NAND gate, I given the input S. Okay, and I taken another gate 2 input NAND gate, I given input R. This gate output I connected to input of this gate, and this gate output I connected input of this gate. So this will become Q, straight to the S Q and straight to the R Q bar. This is the another way of representation. This is also non-gated latch. In this lecture, we'll compare non-gated NAND and non-gated NOR latches. Suppose if we take a NAND, it need two input NAND gates, and a NOR also need two input NOR gates. Okay, number of gates and number of inputs same, but in NAND we use NAND gates, but in NOR we use NOR gates. Okay, we call NAND is active low latch, but NOR is active high latch. Okay, so when we drawing logic diagram in NAND latch, straight to the S we have to connect Q, but in NOR straight to the S we have to connect Q bar. Okay, suppose if we observe the output in NAND, that Q same as the input R, but in NOR Q will be same as input S. Okay, but in S bar R bar latch, Q become same as S bar. Okay, in this lecture we'll discuss about the order of input combinations that we apply to non-gated latches. For example, I take a non-gated SR NAND latch. So it contains two inputs, so we will get to four possible input combinations: 0 0 0 1 1 0 1 1. You may get doubt, do I need to start from 0 0? Can I apply 1 1? Like that you may get doubt. Or can I apply some other combination like 0 1 or 1 0? Suppose initially if you apply 1 1, we cannot predict the output because we don't know the second input of each gate, and there is no output at that time to feedback. So we cannot predict output if we apply 1 1 at the starting. So in that case, we have to apply any of other three combinations, either 0 0 0 1 1 0. We can apply any of combinations because even though we don't know second input and there is no output to feedback, because in these three combinations at least one of the input is 0, so that in NAND gate if one of the input is 0, output will become 1. Like that we can get the output. So we can apply any of these three combinations. But if we apply 0 0 initially, circuit goes into invalid state, unused state. When we maintaining inputs 0 0, how many times you feedback the output, you will get the same output. Okay, so to make the circuit useful or to come out from the valid state, we have to change any one of the input. So if I apply 0 0, I will change this R value, so that combination is 0 1. Then if I change to another combination 1 0, circuit become reset. Okay, so the point is here we cannot apply 1 1, but we can apply any other three combinations. If you apply 0 0, it will go to invalid state. To make it useful, you have to change any one of the input. Okay, in this lecture we will discuss about non-gated latches with unequal delays. Whatever the non-gated latches we discuss, those are without delays or with zero delays. Okay, so whenever the gates has equal delays, the working will be same as without delays. So the non-gated latches working without delays and with equal delays will be same, but when the gates contain unequal delays, the working will be different. Okay, for example, this is the SR non-gated NAND latch. It contains two NAND gates. This gate may have some propagation time, and this gate may have some other propagation time. Okay, for example, this top gate may have 3 nanoseconds, this below gate may have 5 nanoseconds, or this top gate may have 5 nanoseconds, this below gate may have 3 nanoseconds. It means they both may contain different delays. and one can be greater than other, or other can be greater than another. Okay, that is the situation. So in this case, how to analyze the working, that we will see now. Okay, let us discuss first condition. When we apply 0 0, what happening? Suppose with equal delays or without delays, how we doing? When I apply 0 0, I am checking the output of both gates at a time. Okay, but when unequal delays, we should not check like that. What we have to do? Suppose now here I applied 0 0, S0 or 0, and the outputs are Q Q bar. Okay, so here I take in the top gate has less delay, so it is speeder than below gate. So whichever the gate is faster or less delay, first we have to take the output of that gate, because it will give the output first than other gate, na? Okay, right. So this is 0. If any input is 0, I will get 1. Okay, this is I am showing in this diagram. Next, in this diagram, this whole all diagrams are for first condition 0 0 only. Okay, so here input 0 0 only. Now we got this Q first, so I will feedback this output now to here. Now if any one input is 0, I will get 1. So Q bar is 1. So this is the difference with unequal delays. So you have to get the output of faster gate first, then you have to feedback that output to another gate input. In that way we have to do. Suppose if this below gate is faster, first I have to predict Q bar, then I have to feedback this Q bar to above gate. Okay, right. So finally with 0 0, I will get Q bar 1 1 only, even though I feedback many times. When I am maintaining input 0 0, even though we feedback this outputs many times, we will get same output 1 1 only. So this will be invalid. In without delays case also, we will get same invalid only. But here, what's the difference? How you taking the output and how you feedbacking, that differs. Okay, we'll see remaining conditions also. Now we'll see second condition, what happening when I apply S0 R1. So when I applying S0 R1, already the existed outputs are 1 1, Q1 Q bar 1. Okay, so here gates have unequal delays, so first what I have to do, I have to feedback the faster gate output. So this Q I have to feedback here. So now they both are 1 1. This gate inputs 1 1. Okay, so that what I will get? I will get 0. But already here Q bar 1 existed. So this Q bar existed output, and now the output I got here. Okay, now here there are two outputs now. So first this existed output I have to feed back to this gate. So I fed back this existed output 1 to here. Okay, now if any one input is 0, then I will get 1. Okay, then again I have to feedback this 0, because this is also output now. When I feedback that 0, now also I am getting 1. So this one I am getting with feedbacking this 0, and this one I am getting when feedbacking this one. Okay, so both are 1 1 means I am getting 1. Okay, suppose now if I feedback this one again to this gate, below gate, I will get 0. Okay, so here I am getting Q1 Q bar 0. Okay, but this output, whether it is stable or not, to know that again I will feedback. Okay, this 1 I fed back here, so I am getting 0. Again this 0 I will feed back to this. I am getting 1. So it is maintaining stable. This will be the final output. When I apply S0 R1, I am getting Q1 Q bar 0. Okay, it is also same as without delays, but here we are feedbacking faster gate output first, then slower gate output later. But in without delays, we will check both outputs at a time, na? We will feedback both outputs at a time, na? Okay, that's the difference. Now we'll see another combination. Now we'll see third combination, S1 R0. Here I am getting Q0 Q bar 1 output. When I check for stability also, same I am getting. It is also like without delays. Okay. Now last combination with 1 1 I am getting hold. Okay. So these all combination I checked with unequal delays by assuming upper gate is faster than below gate, and you have to check what happening when upper gate is slower than below gate. Okay, that also you have to check. And finally you may think even with delays, that also unequal delays, this operation or output is same as without delays only, but sometimes you may get different behavior. Suppose here you are applying 0 0, okay, and you are getting invalid output. Second I applied 0 1 condition, okay. Suppose second you apply 1 1 condition as second condition. When you apply 1 1, keep upper gate faster, then check the output. And you apply same 1 1, now keep below gate faster, then check the output. In these two conditions you will get a different output. Okay, that makes the difference. Okay, right.
In this lecture, we will discuss about SR NAND gated latch. That also positive level, with a positive level. Okay. So this is the symbol. So it contains three inputs. Two are data inputs SR. One is control input. We can call it as enable or clock. It will work with the clock levels. Okay. So here we take in positive level means its value will be 1. Clock or enable value will be 1. It means it is working with positive level trigger. Okay. Their outputs are 2, Q and Q bar. Okay. So we have to write straight to S Q. In the diagram also straight to S Q. So why it is called gated latch, we'll see. Okay. So whatever the input side, two NAND gates are there, these are called gated part or driving part. And these last output side, two NAND gates are called latch part. This two NAND gates nothing but non-gated latch part. Okay. Suppose if you take a bus, driver will be at the starting. So that's why this is called driving part or gated part. Okay. This is the latch part. So latch part at output side, driving or gated part at input side. So in the non-gated latches, these gates are not there. That's why that is called non-gated latch. Okay. Right. See the construction here. Yes, we connected to this, or we connected to this gate, and the clock is common to both gates. Okay, this is the construction. Now we'll see the working. So before going to further process, we should have this latch truth table. This latch is a non-gated SR latch. So that truth table we should have. So I taken the truth table in a simplified way. So we know from the non-gated SR NAND latch, when inputs are 0 0, we get invalid. When inputs are 0 1, it means S0 or 1, we get set 1. And when S1 or 0, we get reset 0. And when both inputs are 1 1, it will be hold. Okay. So in any gated latch or flip-flop also, the design process is after drawing this symbol and logic diagram and this latch truth table, non-gated latch truth table, then we have to do characteristic table, then we have to do excitation table, then we have to do characteristic equation. These are the steps. Okay. So this is step 1. This is step 1. This is for step 2, not step 2. This is for step 2. Then this is step 2. Then step 3. Step 4. So these all 4 steps are common to gated latches and flip-flops also, for both any gated latch and any flip-flop. Okay. Now we'll see how to do characteristic table. So in the characteristic table, generally we take the inputs and present state and then we predict next state. Okay. So here the format is we take enabler clock. So I mentioned this is positive level. So positive level means it will work whenever we apply 1. Okay. And we will see what happen when we apply 0 also. For positive level, if we apply 0, what will happen? 0 means negative level. For positive level circuit, if we apply negative level, what will happen? And for positive level circuit, if we apply positive level only, then what will happen? Both will see. Okay, right. Suppose when I apply 0, it means for a positive level circuit, if I apply negative level, whatever the data inputs, SR can be any value. It can be 0, 0, 0, 1, 1, 0, 1, 1, and QN value also can be any one. Whatever it may be, it will become hold. Okay, Qn n plus 1 become Qn only. Okay, so here in this condition, circuit is not triggering, because post not triggering means positive level circuit will respond to only positive level, not to negative level. It is not responding or not triggering. However, it is in previous, it will be like that only. There is no change in the circuit. That's the meaning. Okay. Now we'll see what will happen if we apply positive level. Okay. So how to write this S value, R value, Qn value, we'll see. Suppose there are two inputs, means 4 combinations, 0, 0, 0, 1, 1, 0, 1, 1 will come. So this Qn can be 0 when inputs are 0, 0. Or it can be 1 also when inputs 0, 0. And Qn can be 0 when inputs are 0, 1. Or it can be 1 also when inputs are 0, 1. Like that, Qn can be 0 when inputs are 1, 0. Or it can be 1 also for 1, 0. And finally, Qn can be 0 for inputs 1, 1. And it can be 1 also for inputs 1, 1. Okay, like that we have to write. In any gated latch or any flip-flop, we have to write like this only. Okay, right, remember. Now we'll see Qn n plus 1 values and state values, state names. Okay. So here now I am applying S equal to 0, R equal to 0 and clock value 1. Then what will happen? Go to the circuit diagram. Here it is 0, here it is 0, here it is 1, here it is 1. It means if any one input is 0, output become 1. Any one input is 0, output become 1. It means 1, 1 are going to non-gated latch. When 1, 1 going to non-gated latch, see what will happen? Hold will happen. This hold will happen. So circuit will become hold. It means n plus 1 become n only. What is the n value? When we apply S0 or 0, n value is 0, so n plus 1 0. And n value 1 also. So that's why n plus 1 value also becoming 1. So this is called hold. 0 is there, 0 is coming, so hold. 1 is there, 1 is coming, so hold. But what's the difference between this hold and these two holds? This hold is happening because of no change in the circuit. No change means circuit is not responding. Okay. However, it is in previous like that only. But here it is responding, but it is giving same as previous output. But here it is responding. That is the triggering. That is the meaning of triggering. Okay, that you have to observe. Now we'll see next condition. What happening when we apply S0 or 1? S0 or 1. We'll go to diagram and we will check. So here I applying 0 and here 1. Clock is 1 1. Okay. So if any one input is 0, so it will become 1 here. Here below both are 1, so it will become 0. So it means 1 0 is going. When 1 0 going, what is the output? See here. 1 0 going, what is the output? Reset. Reset value is 0. So reset. Okay. Here reset coming. So reset means value 0 0. In both cases 0 0. Okay. Once observe, this 0 1 is going to gated part, not to latch part. But latch part is getting 1 0. Okay. That's why reset. That you have to observe. Okay. Next condition. In this case, similarly, you can apply driving part getting 1 0, but latch part will get to 0 1. When we get 0 1, we know it will become set. Then 1 1 is happening. Latch driving part getting 1 1, but latch part 2 getting 0 0 at input. So it will become invalid. So invalid X means here what you have to observe. Here X means 0 or 1. Here X means 0 or 1. Here X means 0 or 1. And here what it means, here invalid means this Q1 plus 1 value and Q1 plus 1 bar value both are same. That's the meaning. Okay. Now we'll see excitation table. This is step 10. So in the excitation table, we write n to n plus 1. This n is the present state, n plus 1 is the next state at input side, and we will predict what can be the SR values, input values. When we get n plus 1 these values, what can be the SR values, input value. Like that we do excitation table. Okay. So if there are two inputs means 0 0 0 1 1 0 1 1 will come. 4 combinations. So now how to write this SR values in excitation table we'll see. So what is the n plus first value combination? 0 0. Now go to characteristic table. From the characteristic table only we have to write excitation. See n to n plus 1 value here one time 0 0 and here one time 0. Okay. So here in this two, here 0, here this 0 and this 0. What is the S value? 0 only. So S we are getting same value, so it will be 0. But R we are getting different value. See here 0 it is 1. Whenever different value you have to write like X. Okay, so we will get 0x. For 0 0 we will get 0x. Now we will see for 0 1. But 0 1 is there at one place only. See here this 0 1 there at one place. But 0 0 there at two places. That's why we compared. So for 0 1 only what n plus we can simply write S1 or 0. S1 or 0. Okay. Next we'll see 1 0. S equal to Q1 equal to 1 and n plus 1 equal to 0. For 1 0 we are getting 0 1 S0 or 1 S0 or 1. Now we'll see for n to n plus 1 1 1 it will be at two places. So here at one place and here at one place. So here what we getting S value 0 and here we are getting 1. So yes we are getting different but R we are getting same. Okay. Same is what we getting are 0 but S different, so we write X. So like that we have to write excitation table. Okay. Now characteristic table. Characteristic table. So what is meant by characteristic table? We have to determine next state Q1 plus 1 value by assuming data inputs and present state as K-map variables. Okay. So from the characteristic table only we have to do characteristic equation. Here we have to determine this n plus 1 next state by assuming this Qn and SR as K-map variables. Okay, this Qn is also called present state or state. Okay, so whatever the 1 values or x values, okay, if we are doing with SOP map, 1 values or x values, we have to substitute those in the K map and we have to determine the equation. So I substituted and I determined. So I got Qn plus 1 equal to S plus Qn R bar. Okay. So what's the benefit of this one? I can determine Qn plus 1 value by substituting S value and Qn value R value in this equation, right? Okay, that's the benefit. So here, whatever this hold happening, this value is going to this side. Okay, like this, from left to right side they are going. But when we take hold in the non-gated latch, how it happened we'll see. This is in gated latch, but how it happened in non-gated latch, that we'll see. See here, hold is happening from top to bottom like this. Okay, but we no need to remember right to left to top to bottom like that. Just I am showing. Observe the difference. In this lecture, we'll see SR NAND gated latch with negative level. So negative level means here we are applying clock or enable negative level 0. Okay, so it will trigger a response when we apply 0 at clock. So in the symbol we have to show, we have to keep a bubble at clock. Okay, that's the representation. It means we apply outside 0, but inside it will be inverted and inside it will go as 1. Okay, so positive level circuit respond when we apply 1. It will become hold when we apply 0, but a negative level circuit will become hold when we apply 1, but it will respond when we apply 0. Okay, that we have to observe. We'll see. This truth table is the latch part, non-gated truth table that we know. This is the characteristic table. Next excitation, then characteristic equation. This characteristic equation, this excitation table will become same as positive level only. No difference. Okay. Only in the characteristic table we can see the difference in this part, only clock part. Remaining everything same. No difference. So here for negative level, if I apply 1, it will become 4. But if I apply 0, it will respond. But this 0 is becoming invert. Okay. Suppose when I applying 0, 0, SR 0, 0, what happening we'll see one condition. So here applying 0, 0 and the clock is 0. This will become invert. Ultimately it will become 1, 1. So it is becoming same as positive level only. Okay, right? In this lecture, I will explain both positive level and negative level SR NOR gated latches. Okay, separately. Positive level and negative level separately. Okay, first we will discuss positive level. So here why the name NOR latch came? Because latch part is NOR. If this latch part is NAND, it will become NAND latch. Why gated? Because to that latch, there are some driving or gated part is attached at the input side. That's why. Okay. And one more thing we have to observe between gated NAND and gated NOR. In gated NAND, latch part is NAND and driving part also NAND. But in gated NOR, latch part is NOR, but driving part is AND, but not NOR. Okay, remember this. This is applicable to any other latches, gated latches and flip-flops also. Okay. So why we using AND gates here? Because we changed latch to get the same output as gated NAND latch, we have to change these gates. That's the reason. So ultimately, whether it is a gated NAND or gated NOR, the output should be same. Whether it is a gated NAND or gated NOR, it is a latch only, gated latch only. Gated latch means that should behave same even we change the latch part. Okay, changing the latch part is a different way of construction, but ultimately the functionality of gated latch should be same. To make the gated latch functionality or behavior same, okay, we are changing the gates in the construction. That's the reason. Okay, but if we take non-gated NAND NOR, they both behave different. The truth table will be different. Okay, that's the drawback there. Okay, some more drawbacks also there with latches. I will discuss later. Okay, so symbol will be same as NAND latch only. Only this logic diagram is changing. Okay, and the remaining all steps and this truth table will change. Latch part truth table because this is now NOR latch. Okay, but remaining this step 2, step 3, step 4, everything is same. No difference. Okay, we'll see one input. Suppose when I apply 0 0 and with positive level clock is 1. So then what will happen here? I am applying 0 0 and this is 1. It means 0 1 1 0. If any input is 0, and gate will become output becomes 0 and here also output becomes 0. Okay, so what going to NOR latch? 0 0 is going. When 0 0 is going, what will become NOR latch? Hold. Okay, same happening. We do like that. However, we got with gated NAND latch with positive level, like that only we can get. Okay, there is no other difference. Now we'll see negative level. Only here we have to keep inverter and here we have to keep bubble. Remaining everything same. Remaining all same as positive. No other difference. Only in this table we know these values will change. Clock values. Okay, right. In this lecture, we'll see the working of de-gated NAND latch with positive level. We can simply also call it as latch, D-latch. Okay, D-latch always means gated latch. There is no non-gated latch in D. Okay, this is the logic diagram. We can get to D-latch logic diagram from SR latch only. Suppose take SR. So in the SR, this will be S, this will be R. Just interconnect that SR and make it as D. Okay, then SR gated latch will become de-gated latch. But here, if I are using NAND latch part, driving part will come NAND. And when we using NAND latch part, you have to connect inverter here to the R. Okay, that we have to remember. This is the logic diagram. The same logic diagram we can do in another way. Just I replaced this not with NAND. Okay, both are right. This one and this one also right. And I did another way. See here, instead of using inverter, here I am getting this. I am connecting here. Okay, whatever this connection I am connecting here, so it will become same. Ultimately, what we getting will see here. Suppose if I apply 0 here, and if it is a positive level 1, 0 1. If any input is 0, then it will become 1. So here I am applying 0. I am getting 1 inverted. Ultimately, that one only coming here, na? Okay, so if I apply 0 here, I need 1 here. If I apply 0 here, I will get 1 here. That one I can connect here. Okay, so when I apply 0 here, I will get 1. Here I need 1, so that one I am connecting here. So we no need to use inverter in this case. This is also same as above diagrams. Out of these three diagrams, we can use any. Okay, this is the symbolic representation. Okay. Now we'll see the characteristic table. We'll take the clock D, Qn, n plus 1 and state. This is positive level. When I apply 0, next state will be as present state. Okay, whatever the D value or present state values. But when I apply 1, circuit responds. Circuit will trigger at a positive level. Okay. So this Q1 can be 0 when we apply input 0, or Q1 can be 1 also for input 0, and Q1 can be 0 for input 1, and Q1 can be 1 also for input 1. Like that we have to write. Okay. Suppose when I applying 0, what it means? When I applying 0, this is 0, it will become 1. It means we are applying S0 or 1. When we apply S0 or 1 in SR gated latch, what happened? Circuit became reset na? So 0 1, here it will become 1 0. 1 0 means NAND latch will give reset. Okay, that reset we have to write. See here in these two cases reset 0 will come. When I apply 1 here, what will happen? D value. When I apply 1, it will become 1 0. It will become 0 1. When I apply 0 1, circuit become set. Circuit become set. Set means 1. Okay, so we can simply draw logic diagram and characteristic table from the SR gated latch itself. Okay, for D also. This is the excitation table. This excitation table also we can get from this characteristic table. Okay, I told in previous lectures how to get excitation table from characteristic table. Same process. Okay. Here one shortcut, whatever n plus 1, qn plus 1, that will become D. Blindly we can write for D. Okay, not for other latches or flip-flops. Now in the characteristic table you can observe one thing. You can write n plus 1 also blindly, it will become as D. Okay, for these conditions, 4 conditions. Okay. And one more thing we have to observe in logic diagram. Whatever D, that will become S. Straight to the S we have to write Q. If we are using this latch part as NAND. Okay. Finally, we'll see the characteristic equation. I am getting Qn plus 1 equal to D. When I substitute in the K-map, that only happening in the excitation table. Na? Ultimately, in the excitation table and characteristic table also same happening, because ultimately characteristic equation means we have to determine n plus 1. Okay, n plus 1 is nothing but D. Okay. Now we'll see with positive level D gated NOR latch with NOR latch part. Okay, symbol will be same. So here latch part NOR. Whenever this is NOR, I told driving part will be AND. But we have to observe two changes here. Here we have to connect inverter to at R place, not at S place. Whenever this is NOR latch part, this change we have to do. Okay, and straight to the S we have to write Q bar. That also. This is common. This is applicable everywhere, we know. Okay, right. Now characteristic table will be same as the previous. Excitation table will be same as previous. Characteristic equation also will be same as previous. Now we'll see with NAND negative level. Negative level means you just here you have to connect inverter. In the symbol you have to keep bubble here. Okay. Characteristic table, simply here this clock values we will change. Here previously 0, now it will become 1. Here these all becomes 0. Previously all are 1s. This is only change. Everything same. This is same. This is same. Now with negative level NOR. Okay, here we keep inverter and here we keep bubble. Okay, now just this is same as previous, and this is same as previous, and this is same as previous. Okay, before watching this lecture you should do watch SR, gated non-gated latches, then only you can understand this. Okay, right. In this lecture we'll discuss about JK latch, nothing but JK gated latch. There are no non-gated latches in JK. Okay, first we'll discuss with the positive level. This is the diagram. We can get this diagram from SR only. Okay, first to draw SR, you know how to draw, and name this SR S as J and R as K. Then connect this Q to here and connect this Q bar to here. Okay, or we can do another connection also. So this we cannot give here, and this connection we can give here. We can do like that also. Okay, so from SR only we can get JK. This is the symbolic diagram. Okay, and this is with NAND latch part. Then we'll see the characteristic table. This characteristic table almost same as SR characteristic table, only when J equal to 1, K equal to 1. Here only change will come. So here what will happen in SR? Invalid happen. Here toggle will happen. Toggle means if the present state is 0, toggle means 1, like a complement. And the present state is 1, next state will be 0. Okay, but this 0 to 1 and 1 to 0, again it will happen continuously. Multiple complement is called toggle. Multiple and unlimited, that is called unstable output, nothing but racing. Okay, when we apply Z equal to 1, K equal to 1 and clock equal to 1, this JK latch will toggle, okay, continuously. This is called racing. Only this condition is difference compared to SR and JK. Remaining all are same. Okay. This JK flip flop came to avoid this invalid condition, because in SR this state is unused state. So we want to make it use. That's why JK came to make it useful. But in the JK we made it useful, but we are not getting a stable output. Okay, that is the drawback. So the JK advantage is avoiding invalid condition of RS, and the JK drawback is getting unstable or racing output. Okay, next, excitation table. You know how to do this from characteristic table. I explained in previous lectures. This is the characteristic equation. Okay, you know how to do it also. I explained previously. Now coming to negative level uh, JK latch. Okay, with an AND latch part. So here NOT gate will come and here bubble will come, that you know. Here once observe, with an AND latch part always we write Q straight to the Z, that you have to remember. So this characteristic table same as previous. Okay, just here previous is positive level, this is negative level. Just these values will we have to change, you know that. Okay, excitation table and characteristic equation same. Now coming to NOR. Okay, with NOR latch part. So here with respect straight to the J we have to write Q bar, that we have to observe. And this is same as positive with an AND. Okay, no other difference. This is same as above, this is same as above. With negative level, same NOR latch part. Here we keep bubble and here inverter. This is same as negative level with NAND. Okay, this is also same, this is also same. Okay, to understand these or this topic, you have to see previous lectures from the flip-flops and latches starting. Then only you can understand it properly. Okay. In this lecture, we'll discuss about T-latch, T-gated latch. There are no non-gated latches in T. Okay. So this is with the positive level and with the NAND latch part. We just to interconnect J and K. From the JK only we get T. We just interconnect J and K and we'll name as T. Okay. But here we don't use any inverter in the JK connection. Okay. As we connect to SR and to make a D by connecting inverter like that, here we don't use any inverter. Okay. That you have to observe. Next, this is a characteristic table. Okay. So here in the characteristic table, if you are applying T equal to 0 means J0 K0. What will happen when J0 K0? Hold will happen. That's why hold. And when T equal to 1 means J1 K1. What will happen? Toggle will happen. Okay. Hold means this 0 I am writing as it is, 1 I am writing as it is. This 0 becoming 1 and 1 becoming 0. Okay. Here also toggle means race condition. This is the excitation table. One thing we can observe in excitation table, here when we apply XR operation to Qn and Qn plus 1, it is this T is matching to XR output. See here same 0. Below also same 0. But the second and third condition 0, 1, 1, 0 different. So we are getting 1. Okay. That we have to observe. And this is the characteristic equation. Here also we are getting Qn plus 1 equal to T XR Qn. Okay. Right. Now we'll see negative level with NAND latch part. Okay. Here we use this bubble and here not get that And in the characteristic table here we write 1 and here zeros. Okay. Remaining everything same as previous. Excitation table and characteristic equation same as previous. Now we'll see with positive level with NOR latch part. Okay. This circuit will change. Then here positive level means here 0 and these all are 1s. Okay. Remaining everything same. Excitation table, characteristic equation same. Okay. So this is characteristic equation, not table. Equation. Previously also what is there? Equation. Okay. Right. Now this is with negative level NOR latch part. Here bubble will come and here not get. So here we are getting 1 and here zeros. Excitation table and characteristic equation all are same. Okay. In this lecture we'll discuss about SR flip-flop. We'll discuss with NAND latch part and NOR latch part also. With the NAND latch part again we'll discuss with the positive edge and negative edge. And with the NOR latch part also we'll discuss with positive edge and negative edge. So flip-flop means edge triggered or edge sensitive device. Okay. We can call this circuit also called as edge triggered gated latch. Edge triggered gated latch nothing but flip-flop. But level triggered gated latch is not a flip-flop. Okay. Right. So first this is with the NAND latch part and with the positive edge. This is the diagram. So this diagram same as this gated latch with the positive level. Okay. So in the symbol here we have to keep some that like this triangle symbol. It indicates edge triggered. Okay. Right. Okay, this is the latch part truth table. This is the characteristic table. Here, only one difference in this here. So here, this 0 means positive, negative edge. It means it is changing from 1 to 0 transition. Okay, and here 1 means positive edge. So it is changing from 0 to 1 transition. So here, these ones we generally represent with a rising arrow. The 0 with a falling arrow. That's the representation for flip-flops. So this one representation, and in the symbol, this triangle representation, this will come to the difference between gated latches and the flip-flops. Okay, remaining everything same. Excitation table same. Characteristic equation table same. So you have to watch this lecture after watching gated latches. NAND latch, NOR latch with positive level, negative level. Okay. Now we'll see with negative edge. NAND only with negative edge. See here for negative edge, here we have to keep inverter in the logic diagram, and here we have to keep a bubble along with a triangle. Bubble at the outside, triangle inside. Okay, these are the differences. This is the latch truth table. This is the excitation table, a characteristic table. So in this characteristic table, here one will come. It indicates positive edge. Here zeros will come. It indicates negative edge. Okay, remaining all same. Excitation table same, characteristic equation same. Okay, now we'll see with the NOR latch with the positive edge. Okay, so this diagram change. Here triangle will come. Okay, this is latch part truth table. So this is same as whatever we did with the positive level NAND. Okay, this is also same. This is also same. Now with negative edge with the NAND, negative edge with this is NOR. Okay, we'll check once previous also. Okay, NOR. So negative edge with NOR. So here circle will come and here inverter will come. Okay, latch part, and this will be same as a negative NAND. Remaining everything same. Okay, completed. In this lecture, we'll see the use of SR flip-flop. So ultimately, this flip-flop is a 1-bit storage element. We have to store bit 1 and bit 0. So in the set condition, we are able to store 1, and in reset, we are able to store 0. So it is storing 0 and 1. It acts like a memory element, 1-bit memory element. Other flip-flops also giving set and reset possibilities, not only SR. Okay, right. In this lecture, we'll discuss the drawback of SR flip-flop. The drawback of SR flip-flop is when we apply S equal to 1 or equal to 1 and the clock is asserted, we will get invalid output. Okay, n plus 1, qn plus 1 and qn plus 1 bar both become same. Both outputs should be complementary, no? So it is violating that rule. That's why invalid or unused condition is the drawback of SR flip-flop. To overcome this, we went to JK flip-flop. Okay. In this lecture, we'll discuss about D flip-flop, that is also with the positive edge and with NAND latch part. This is the logic diagram. Same as latch, D latch. Okay, just in the symbol, we have to keep this triangle symbol. Okay. Next. This stochastic table also same, just latch will work with levels, but this will work with the edges. So here 0 means it is working during 1 to 0 transition. Here 1 means it is working during 0 to 1 transition. Okay, remaining everything same. Excitation table same as latch. Characteristic equation also same as latch. Coming to D flip flop with NOR latch part, positive edge only. Okay, this is also same. This is also same. This is also same as previous. Okay, only in the logic diagram we can see the changes in gates. Okay, remaining everything same. Now coming to a D flip flop with negative edge with an AND latch part. Okay, so here in the symbol you will get a bubble outside along with the triangle symbol, and here we get NOT gate that we know. Okay, so here 1 means 0 to 1 transition, 0 means 1 to 0 transition, remaining everything same. Excitation table same, characteristic equation same. Okay, now with negative edge NOR latch part D flip flop, logic diagram will change. Okay, then symbol will be same, characteristic table will be same, excitation table will be same, characteristic equation will be same. So to understand this lecture very well, first you have to see a D latch. If you want to understand D latch, you have to see before lectures. SR latch, SR flip flop, gated, non-gated latches, those you have to see. Okay, I already uploaded, you can go through, then you can understand this very easily. In this lecture we'll discuss the necessity of D flip flop. You know, we get D flip flop from SR only by interconnecting JK and connecting one inverter at suitable place. So this D flip flop ultimately developed for the implementation of shift registers. You know, in the shift registers the input and output data should be same. Okay, in that case only D flip flop suitable, no other flip flop will produce same output as input. Okay, in the shift registers we want to shift that same data but after some delay from right to left or left to right. Okay, so this D flip flop exclusively implemented for shift registers and for some counters also. Some counters means like ring counter, Johnson counter. Those two counters also called shift registers counters. Okay, there also we use D flip flop. Right. In this lecture we'll see about JK flip flop with NAND latch part and with positive edge. Okay, here triangle will come, remaining everything same as latch, JK latch. This table same as latch. Okay, latch will work with levels, it is working with edges. Okay, that you have to know. Excitation table and characteristic equation same as latch. Now with the negative edge, with the latch part, NAND latch part only. Negative edge means here bubble will come along with this triangle. Okay, and here inverter. This is same as latch only, just it is working with edges, that is working with levels. This is same as latch, this is same as latch. Now with NOR latch part positive edge, the circuit will change, you know, and here triangle will come. This is same as latch, that is working with the levels, it is working with edges. This is same as latch, this is same as latch. Now with the negative edge, NOR latch part. So here circle and triangle will come and here NOT gate will come. Okay, so this is same as latch, just that is working with levels, this is with edges. Okay, excitation table and characteristic equation also same. Okay, so if you want to understand this properly you have to see from starting of the non-gated latches, then gated latches. Okay, SR, D flip-flop. Then you have to come to JK. Then you can understand well. Okay. In this lecture, we'll discuss about the necessity of JK flip-flop. First we implemented SR flip-flop. SR flip-flop providing set and reset, we are able to store 1 and 0. Okay. But in SR flip-flop, one state is unused state. Okay, invalid state. That we want to make it useful. That's why when we try, we implemented JK. Okay. So the drawback in SR is invalid. So the drawback is overcome by JK. But again, in the JK, whatever the output we are getting, that is not stable. Okay, that is the drawback. It overcome invalid, but it is getting unstable output. Okay. So ultimately, we developed JK to avoid invalid state in RS. That's the necessity. In this lecture, we will see the drawback of JK flip-flop. So in JK flip-flop, when clock asserted and when J equal to K equal to 1, this output changing continuously, complementing multiple times. This is called racing. This is the drawback. To overcome it, we implemented master slave JK. Okay. In this lecture, we'll see the meaning of toggle or invalid state or unstable state or racing. In JK flip-flop, when we apply clock is asserted and J and K both are equal to 1, this present state will become toggle in the next state. Okay, but this one won't be like a 1 after toggling one time or complementing one time. It will change continuously, 0 to 1, again 1 to 0, 0 to 1, like that. This one also will change. Okay, so that continuous complementing is called a toggle. Continuous, repeated, or unlimited complement is called a toggle. Here we are showing only one time, but in the reality, it will change multiple times. There is no ending until we on the circuit apply the inputs 1 1. Okay, so output is continuously changing. It is not stable or unstable condition. Okay, they're changing 1 to 0, 0 to 1. That's called racing or race around condition. Okay, this is a drawback only. That is also in JK flip flop. We'll see in further lectures how to avoid this drawback. Okay, we use master slave. We'll see in the master slave how it is avoiding. In this lecture, we'll discuss about T flip flop with the NAND latch part, that also with the positive edge. Okay, here you can see triangle symbol compared to latch, remaining everything same. Now this is characteristic table. Now these clock levels are working with edges. In latch, they will work with levels. Okay, excitation table, characteristic equation same as latch. Now with negative edge, here NOT gate and here circle and triangle symbol will come. So here clock values working with edges. Okay, but in latch it work with levels, remaining everything same. Excitation table, characteristic equation. Now with the NOR latch part, that also with the positive edge, here gates will change and here triangle symbol will come. Now these working with edges. Excitation table and characteristic equation same as latch. Now with the negative edge, NOR latch part, here NOT gate and here circle and bubble and triangle symbol will come. Here it will work with edges. Okay, excitation table and characteristic equation same as latch. Right, complete. In this lecture, we will see the necessity of T flip-flop. You know, in counters, we need T flip-flop. For example, synchronous counters, asynchronous counters, mod counters, up counters, down counters. Okay. In these counters, we need hold nature and toggle nature. Then only particular count will happen. Okay. So particularly for those counters, we need T flip flop or JK flip flop, but we mostly use T, because in JK, along with the toggle and hold, set to reset is there. That set to reset we don't need in the two counters. Okay. There are some other applications of this T flip flop also.
In this lecture, we'll discuss the difference between characteristic table and excitation table. So, in the characteristic table, we will determine the next state value from the data inputs and present state. But in excitation table, see here, we will determine the input values, data input values from the present state and next state. Suppose for these present state and next state, what can be the input values? Like that. Okay. In this lecture, we'll briefly discuss about master slave JK flip flop. There are master slave D, master slave SR also, but we are interested about master slave JK because this flip flop came to avoid the drawback in normal JK flip flop, that is racing. Okay, that's why we are interested to know about master slave JK. This is the logic diagram. This master slave JK contains two JK flip flops. This one at the input side is called the master JK flip flop. This flip flop at the output side is called slave JK flip flop. Why this is called slave? Because this is working based on the output of a master. It's depend on the output of a master. That's why this is called slave. Okay. And this master is a positive triggered flip flop. This slave is a negative triggered flip flop. Because we are giving, see here, clock directly to the master, we given positive clock, but same clock we will give to the slave flip flop through the inverter, so it will become a negative triggered flip flop. Okay. And one more thing we have to observe here, for the master we removed the feedback, but there is a feedback from slave output to master input, that you have to observe. And here we used NAND latch part. Suppose if I use NOR latch part, the gated part will become AND and the latch part will become NOR. In that case, this feedback connections we have to change accordingly. Okay, that we have to remember. So this master flip flop will work for positive. This is positive triggered and this is for negative triggered. It means for positive, master flip flop will respond. It will send input to output. Okay. For positive trigger, slave flip flop will become hold. Okay, it won't respond. Similarly, for negative trigger, master will hold, it won't respond, but a slave will respond, it will send input to output. So with this kind of arrangement, we are able to avoid the racing. That is the logic behind to avoid the racing. Okay, so this master slave flip flop is called a pulse triggered flip flop, because during positive this master is working, during negative slave is working, together in total pulse whole circuit is working. So the final output become the slave output and the input become the master input. Okay, right. In this lecture we'll discuss about flip-flop conversion, necessity of flip-flop conversion, that is why we doing conversion, and we will discuss the flip-flop conversion process also, steps. Okay. First we'll see the necessity. I will give you one example. Suppose I want to design serial adder. I want one full adder and one D flip-flop. I have full adder but I don't have D flip-flop, I have T flip-flop. So in this case, what is the options? What are the options? I have to go and buy D flip-flop. That is one option. And another option is, if I able to convert or utilize that T flip-flop into as a D flip-flop, then I no need to buy. This is the second option. Okay. So the flip-flop conversion is about how to utilize the existed flip-flop by making or converting it into required flip-flop. Okay, that's the intention. So we can do nearly 12 types of conversions. We can do T to D and vice versa, T to SR and vice versa, T to JK and vice versa. Then D to SR and vice versa, D to JK and vice versa, SR into JK and vice versa. Total 12 conversions we can do. Okay. Given or existed flip-flop, two names, required or desired flip-flop. Okay. So now we'll see conversion process. There are three steps. In the first step, we have to mix the characteristic table of required flip-flop and excitation table of given flip-flop. We have to mix both as one table. So here Qn and Qn plus 1, present state and next state, will be common to both characteristic table and excitation table. Suppose if Qn and Qn plus 1, any one or both contain X, in this case the given flip-flop data inputs become X. That is the first step. Now second step, we have to determine the simplified equations for data inputs of given flip-flop. Okay, by assuming required flip-flop data inputs and present state as K-map variables. Okay. Then in the third step, we have to draw the given flip-flop symbol, because we have that only, that flip-flop only, na? So we have to take the given flip-flop symbol and we have to make it as required flip-flop from the simplified K-map equations. Okay. So in this given flip-flop symbol, the outputs are present state and its complement. Okay. So in further lectures, I will take two examples. I will show each step how to do. Okay. In this lecture, we will discuss the conversion process of T into D flip-flop, T to D conversion. Okay. So this is the step 1. I told in the previous lecture, in the first step, we have to take the characteristic table of required flip-flop and the excitation table of given flip-flop. So here given flip-flop is T and the required is D. So I taken D flip-flop characteristic table and T flip-flop excitation table and I mix it together. Okay. So this D Qn n plus 1 become the characteristic table of D. This Qn n plus 1 and T, these will become excitation table of T. So here present state and next state will be common to both. Okay. This is the step 1. Coming to step 2, I told we have to simplify this data input value of a given flip-flop T. Okay, by assuming required flip-flop data input and present state as K-map variables. Okay, so D and Q1 are K-map variables, so we need two variable K-map and we have to determine the simplified equation for T. Okay, that we have to do. See, this is the simplified equation for T. What is the T value? D XR Q1. It means D bar Q1 plus D Q1 bar. Okay, this is the second step. Now in the third step, what we have to do, we have to take the given flip-flop symbol. What is the given flip-flop T? It will contain T, clock, Qn, Qn bar. I told we have to assume present state and its bar as outputs of given flip-flop. Okay. Then what is this T value? I got D Qn, XR of D and Qn. So I take an XR gate, I given D here and I given Qn here. Okay. Then it will become as D flip-flop. This is the flip-flop conversion process of T into D. In this lecture, we will see the flip-flop conversion process of JK to SR. Okay, this is the step 1. I told we have to take a characteristic table of required flip-flop and excitation table of given flip-flop. SR is the required, JK is the given. So SR given n plus 1, this part will become characteristic table of SR. Qn plus 1 Jk will become the excitation table of Jk. So here present state and next state will be common. One thing you have to observe here, whenever x came in present state or next state or both, this data input values of given flip-flop become x. See here x, 0, x. Then we have to blindly write xx in the data inputs. Here also 1x. Any one or both is x, then we have to blindly write x in the data inputs of given flip-flop. That you have to remember. Okay. Then second step, we have to determine the simplified equation for this given flip-flop data inputs for j and k by assuming required flip-flop data inputs and present state as k-map variables. So S or Qn become k-map variables, so we need 3 variable k-map to determine j and to determine k. Okay na? Now j will become S, k will become R. Okay. Then in the third step, we have to take the given flip-flop symbol. What is the given flip-flop? Jk. And we have to make it into as required flip-flop by using these simplified equations. So what is the j value? S. What is the k value? R. If I connect like that, it will become as what flip-flop? SR flip-flop. I taken jk, I made it into SR flip-flop. Okay, this is the conversion process. This how to get characteristic table, excitation table, I explained in the flip-flops lectures. Okay, go through that. In this lecture, we'll discuss the differences or comparison between gated latches and flip-flops. Nothing but latches and flip-flops. If we take latches, they work with level triggering. Okay, so latches are level triggered and flip-flops are edge triggered. This is one difference. And we can also say latches are asynchronous because of level triggering and flip-flops are synchronous because of edge triggering. Of course, master slave flip-flops we can call as pulse trigger. They also synchronous. Okay, so this is another difference. If we take latches categories, SR, D, JK, T will come. But if we take flip-flops, there is SR, D, JK, T, master slave JK, master slave D, and master slave SR. Okay. If we take logic diagrams same for both latches and flip-flops. But if we take a symbolic representation, it will differ. In the flip-flops, we will get a triangle symbol. But there is no triangle symbol for latches. Okay. Excitation table and characteristic equation same for both. And if we take characteristic table, almost same. Just in the clock part, we will represent with clock transitions for flip-flop, but we will represent with the levels for latches. Okay, remaining everything same. Even for levels or edges, the values become same. Okay. and if we connect two latches back to back, it will become a flip-flop. It will work as a flip-flop. Okay. And latch is a half cycle storage device and flip-flop is a full cycle storage device. So because of this full cycle storage, static timing analysis is easy in the physical design. So to set up and hold time, engineers will get physical design engineers will get enough time, sufficient time to set up and hold time, because full cycle storage is available with flip-flop. But STA will become, static timing analysis will become difficult. Only half cycle is available to set up and hold time. So STA become more difficult in latch. So these are the comparisons. In this lecture we'll discuss about level triggering, edge triggering, pulse triggering and no triggering. Suppose if we take non-gated latches, they won't contain clock, so there is no triggering. Those are example for no triggering. And if we take gated latches, it will contain clock or enable, so there is a triggering and they work with level, so level triggering. If we take flip-flops, they contain clock and they work with edges, so edge triggering. And if we take master slave type flip-flops, they contain clock and master part will work with one edge and slave part will work with another edge. So whole pulse, the total clock pulse, positive and negative, both are contributing in the circuit operation. That's why they called pulse triggered circuits. So non-gated latches are examples for no triggering, gated latches for level triggering, flip-flops for edge triggering, master slave flip-flops for pulse triggering. Okay. In this lecture we'll discuss about clock and reset, the purpose of clock and reset, and with respect to reset we will also discuss about active high or positive reset, active low or negative reset, and we'll also discuss about synchronous reset, asynchronous reset. Okay, first we'll see about clock. So clock is for timing or synchronization. For example, for a flip-flop, even we apply data inputs, we can see the change in the output, or we can get the output only at particular clock edges according to the data input. Okay, so that timing or synchronization is given by clock. Okay, that is the purpose. And coming to the reset, this reset sometimes we can also call clear. Okay, because it is clearing the already existed output. That's why clear or reset. So this reset is to bring the circuit to the known state. Okay, for example, there is a flip-flop. I am applying some data input. At the time of applying data input, that flip-flop already contains some output. That is called present state. So I don't know what is that output, existed output, present state. So I want to bring that present state into known state. So if I apply reset, that present state will become 0. Okay, it will become a known present state. So now I am applying data input. I know that data input and I know the present state also, because I made it to known state, so that I can predict the next state. Whatever the output coming now, that will be the next state. So I can predict my next state. So like this we can bring the circuit into known state. For that purpose we use reset. Okay, so this reset is two types: active high or positive reset or pos edge reset, and another one is active low or negative reset or neg edge reset. Okay, generally we apply reset to the flip-flops. Suppose if we take positive reset, when we apply 1 to the positive reset, circuit will become reset. But when we apply 0 to the positive reset, circuit won't become reset. Okay, for positive reset when we apply 1, that is called reset applied. For positive reset when we apply 0, that is called reset released. Okay. Similarly for negative reset, if we apply 0, it will become circuit become reset. Okay. And synchronous reset means, suppose when we apply reset, if it is a synchronous reset, at the time of applying reset only, if there is a particular clock edge occurring, then circuit become 0 or reset at the same time. But at that time only particular clock edge is not occurring, then it will wait for the coming positive coming clock edge. At that time it will become circuit becomes 0. Okay, so it is sync with clock. That's why synchronous reset. Suppose if we take asynchronous reset, immediately when we apply reset, circuit output becomes 0. It won't wait for the clock edge. That is called asynchronous reset. Okay, so this positive reset can be sync or async. Negative reset also can be sync or async. Suppose if I take positive async reset, when I apply 1, then circuit becomes 0 immediately when I apply reset. Okay, right. In this lecture we'll discuss about setup time, hold time, metastability, clock jitter, clock skew, and duty cycle. First we'll see about setup time. This setup time is the minimum time that data inputs should be stable before applying clock edge, and the hold time also the minimum time that data inputs should be stable after applying clock edge. Okay, so for sequential circuits like flip-flops, we apply data inputs and control input like clock. Okay, so whatever the data we are applying, that data should be stable before the clock edge and after the clock edge for a certain minimum duration of time. So then only that circuit can take the input properly, then only it can produce output properly according to the input. If it is not taken properly, it means if you are not maintaining some minimum time before the clock edge or after the clock edge, it means if we violating setup and hold time both are any one, then circuit may not take input properly, so it may not produce output properly. That uncertain output is called metastable output. We represent that as X. Okay. Now coming to clock jitter. So we know clock edges will occur. So we expect the clock edge at certain time. Because of this jitter, that clock edge may occur before the expected time or after the expected time. Okay, this deviation of occurrence of clock edge with respect to expected time is called clock jitter. It will measure in the percentage, so that based on that percentage how much deviation is happening we can understand, so that we can solve that jitter. Okay, then coming to clock skew. Suppose there is a register, it contains different flip-flops. We are giving common clock to all the flip-flops of that register, so that common clock may reach to the each flip-flop of the register at different times. That deviation is called clock skew. And coming to the duty cycle, suppose if we take a clock cycle, it can contain on duration, off duration. Okay, so the total duration of on time divided by total duration of the pulse will give the duty cycle. It is also measured in the percentage. Okay, so the duty cycle is the percentage of on duration in the total clock cycle. Suppose if we say the duty cycle is 50%, then on duration is 50, then remaining duration 50% will become the off duration. So here the duty cycle is 50% because the on duration is 50% in the whole duration of the clock pulse. Okay, then in that case it will become a symmetric clock signal. Suppose if I say the duty cycle 30%, out of 100% of the signal duration, only for 30% the signal is high, remaining 70% the signal is low. Okay, this is about duty cycle. In this lecture we'll discuss about preset, clear, sync inputs and asynchronous inputs. Whatever the flip-flop data inputs we discussed, S, R, D, J, K, T, those are sync or synchronous data inputs. Preset and clear are called asynchronous data inputs. This preset is also called direct set and clear is also called direct reset. But this clear is not a reset. Okay, remember that. So sometimes we can give preset bar, clear bar also. If we are saying preset bar, clear bar, those are called negative or active low preset and clear. We can give directly preset bar, clear bar without bubbles, or we can give preset and clear with bubbles. Those are called active low or negative preset and clear. Okay, if we are giving only preset clear without bubbles, those are called positive or active high preset clear. Suppose if we take active high, when preset equal to 1 and clear equal to 0, then circuit become set, Q become 1. So when we want to make the circuit set, we have to maintain preset 1 and clear 0 with positive logic. Okay. Suppose when we want to make the circuit reset, then we have to make preset 0 and clear 1. Okay, this is also with positive logic. Okay, and when we give 1 1 with positive logic, then circuit will go to invalid state, unused state. Okay, suppose when we want to allow the circuit to work with synchronous data inputs and clock, then we have to make preset and clear as zeros, both as zeros. Okay, with positive logic only. Okay, so here we can make the circuit set and reset without depending or without syncing with synchronous data inputs like SR, D, J, K, T. That's why these preset and clear are called asynchronous data inputs. Okay, if we are making circuit set and reset based on synchronous inputs and clock, then it will be synchronous data inputs. Okay, in this lecture we'll see how invalid state of RS flip-flop overcome by JK flip-flop. Suppose this is the diagram of a JK flip-flop with NAND latch part. If we remove this feedback from output to latch output to gated part input, if we remove this feedback, this diagram will be same as SR flip-flop. Okay, so by connecting this feedback, we able to overcome the invalid state. But because of this feedback, invalid is overcome, but race condition happened. But anyhow, this feedback from latch output to gated input is the reason for avoiding invalid state of RS flip-flop. Okay. In this lecture, we'll discuss about present state to next state representation. Suppose generally we represent Qn as present state and Qn plus 1 as next state. Okay. Present state means already existed output. Next state means the output we get now. Okay. Sometimes you may confuse what is Qn, Qn plus 1 and what is Q bar. Okay, you may get confused, I will give clarity. Suppose take this diagram. This Q only, it can become present state and it can become next state also. This Q only. Suppose if this is the existed output, it will become this Q become Qn. If this is the coming output, then this Q become Qn plus 1. Okay, whenever this Q became Qn, this will become Qn bar, and whenever this Q became Qn plus 1, this will become Qn plus 1 bar. Okay, in this lecture we'll see the exact difference between toggle and complement. Toggle complement both indicates inversion, converting 1 to 0, 0 to 1. So the complement, the word complement we use in combination circuit, the word toggle we use in sequential circuits. So when we apply clock to the circuit, if complement is happening, that is toggle. Okay. In this lecture, we'll discuss about racing or race around condition, or why racing occurring in JK flip-flop. Suppose take this logic diagram. If we remove this feedback from output to gated part input, if we remove these two feedback connections, it will become a SR latch or SR flip-flop. Okay. So to avoid invalid condition in SR latch, we connected this feedback. So invalid condition overcome, but because of this racing happened. Racing means multiple toggles. Okay. So here race around means because of this feedback connection, they connected around like this. So because of this feedback connection, racing happening, that's called race around condition. Okay, also called unstable condition, unstable output. In this lecture, we'll discuss the implementation or design of latches by using multiplexer. Latches means we implement only gated latches. As an example, I taken D gated latch, and I will implement with a 2 by 1 multiplexer. Okay. These latches can be positive level latch, negative level latch. Both I will implement. This diagram is with positive level latch. This is for negative level latch. You know, this 2 by 1 multiplexer contain two data inputs, one select input and one data output. And this D gated latch should produce two conditions. Output should be same as input, and we should get a hold condition also. Okay. So this is a positive level latch. I assumed the select of multiplexer as enabler clock of latch, and this multiplexer output, data output, I assumed as latch output, uncomplemented output I taken. And out of two data inputs of multiplexer, this data input I connected to latch input D, and this output I fed back to another input to get the hold condition. So this is the construction. Now this is positive level latch because here there is no bubble at the enable. So when I apply 1, what will happen? See here internally I wrote 0, 1. These are select or enable values. So I am applying 1 means I am selecting this D. So this D will go to the output. If this D is 0, I will get 0 at output. If D is 1, I will get 1 at the output. Similarly, when I apply 0, this will be select. What I am getting here? Q. Q I am getting. It means if my next state is Qn plus 1, what will be the output? It will be same as previous state. Okay. Qn. So it means hold is happening. Now coming to negative level latch, here for enable I kept a bubble. That's why it is active negative level latch. When I apply 0, this D will be selected, it will go to the output. When I apply 1, it will become hold. Remember, when you apply 0 here enable, inside also you have to write 0. Okay, right. Now we'll see how to implement flip-flops with multiplexers. Here I take an D flip-flop and I am implementing with 2 by 1 multiplexers. To implement latches I just need one 2 by 1 multiplexer, but here to implement flip-flop I need multiple 2 by 1 multiplexers. So here for D I need two 2 by 1 multiplexers. And I told when I in previous lectures when I compared flip-flop with gated latches, by connecting series connecting of two gated latches will work as a flip-flop. So to implement this flip-flop using multiplexer, I taken here negative level latch and here I taken positive level latch. I connected in series. Okay. So negative level, this is bubble. Okay. So when I apply a clock 0, this 0 D will be selected. It will go to this output. And this clock 0 is coming here. So here I wrote 0. So this will be selected. This will go to output. It means X is D and Q is X. Ultimately Q become D. We are getting same output when I apply clock 0. And when I apply clock 1, circuit become hold. So it is working as a D flip-flop. Okay. See here the output of first this multiplexer we have to connect as input to second multiplexer. And this clock is common to both. But one of the clock should contain bubble. Okay. We can construct this flip-flop in another way also. See here. Here I taken first positive level latch, then negative level latch. But previously I taken negative level first, then positive level. Okay. So here according to this we have to change the internal values. So when I apply clock 1, this D will be selected and I will get final output at Q. But when I apply clock 0, it will become hold. Okay. So according to the circuit, we have to change this clock bubble places and we have to change internal values of clock. Okay. Then only we can get output properly. Okay. Now we'll see how to implement T flip-flop by using multiplexers. Here I need 3 2 by 1 multiplexers if I take a complemented input, but if I take uncomplemented input, then I need 4 2 by 1 multiplexers. Okay. So the easiest way to implement this T flip-flop, we already know how to implement D flip-flop. Okay, take that D flip-flop diagram. What is the D flip-flop diagram? This whole diagram here I represented as this box. Okay, we know how to convert D flip-flop into T. This is the equation when we convert D flip-flop into T. So what I am getting for D, T XOR Qn. I will connect T and Qn to XOR. That XOR output I will give to D. So this whole circuit now it will become as T flip-flop. Okay, and we know how to implement this XOR gate with multiplexer. I implemented, and this D is D only. If you want to replace this D with multiplexers, you can draw this diagram. You can replace this box with this diagram. Now you will get 3 2 by 1 multiplexers, and that 3 2 by 1 multiplexer together will become a T flip-flop. Here I taken T bar directly. If you want to take T only, you can use inverter here. That inverter also you can implement with multiplexer. In that case, you will get 4. Okay. So this is T flip-flop with multiplexers. So here I given truth table also. For this you can observe. Okay. In this lecture we'll see how to implement JK flip-flop using 2 by 1 multiplexers. I need 6 2 by 1 multiplexers. The simplest way is we know how to implement D flip-flop using multiplexer. Take the diagram and we know how to convert this D flip-flop into JK. This is the equation. Okay, so for this D, connect that equation. Now implement this inverter with mux 2 by 1, this 2 AND gates with 2 by 1, this OR gate also with 2 by 1. So this is 1 2 by 1, this is second, third, 4, and it need 2. Total 6 2 by 1 multiplexers we can get. Okay, this is the easiest way of implementation. This box contain 2 2 by 1 multiplexers because we know how to implement D. So this is the D. That whole box indicates this diagram. Okay. Now we'll see how to implement SR flip-flop using 2 by 1 multiplexers. I need 5 2 by 1 multiplexers. You know how to implement D flip-flop? Take the D flip-flop. It will contain 2 2 by 1 multiplexers, we know. And we know how to convert D into SR. Okay. So this is the equation. So connect that equation to this D. Now replace this NOT gate with multiplexer, AND gate with multiplexer, OR gate with multiplexer. Total 3 multiplexers, and this D flip-flop contain 2 multiplexers. Total 5 multiplexers. So for NOT gate, AND gate, OR gate, I given truth tables here. Okay. So this D flip-flop contain 2 multiplexers. This is the equivalent diagram. That box is this diagram. Okay. So this is the easiest way of implementing SR flip-flop using 2 by 1 multiplexers. Okay.